Hey everybody, and welcome to another Jamovi tutorial. In this tutorial, we're going to continue our pamlj power analysis series. And in this episode, we're going to talk about how to do a power analysis for a factorial ANOVA, a factorial design analysis of variance. Oh yeah, all right. Before we jump into that, we are using version 2.7.5. How to add pamlj. Well, here I have it right here. Click on power. You can see pamlj. We're going to jump into factorial designs. Other videos, we talked about correlation, t-tests. We're going through them, although I am skipping order. Maybe I should have done proportions next. Don't worry about it. We're going to do factorial designs in this video. How to add it. You go up to modules. You click on that. Jamovi library available, and you can click on pamlj right here. For me, it's right at the top. I really enjoy that. But in case it's not for you, you can search PAM and it will show up. Look at that right there. So pamlj, power analysis for linear models, Jamovi. All right. So you click on that, you install that, you get it going, and here we go. So we're going to go up to power, again, pamlj. We're going to go up to factorial designs, and it's going to open up our factorial designs. Now we have two things that are different in this module as opposed to the other modules. This one, we can choose data, and we can get expected means in here, which is amazing, right? We can get expected means. So info shows us what we want to do, right? Aim of the analysis, N or power. You cannot do the effect size calculations in this module. You can only calculate a priori sample size or post hoc power. Okay, it's very, very important. Now, if you click on the web manual, it'll take you to the Factorial Designs page here on Marcelo's GitHub. Okay, so here we have a couple of screenshots, and you can get the help page for based on means or based on partial eta squared, which is what we are going to do. It's not yet available like some of the other ones. Based on means, also not yet available. And you can do validation, which is the post hoc power, and he'll have 2 pages associated with that. Nope, they're available. Okay, so you can do, oh, here you go. You can put in means and standard deviations for our factors, right? So, okay, let's go ahead and do it, but follow Marcelo's lead. I'm not actually going to do it. So let's say we have a variable, A1 and A2. The mean is 10, of one, and a standard deviation of 13, and of another group, it is 20 and 13. So that's how you would put in that information. So I guess you don't actually need to have a full data set open. It's not going to be a raw data set anyways, okay? So if we put column A into factors, and our means into means, and our standard deviations into standard deviations, and we use the input, you can see that we need an N of 74. Now, I'm pretty sure the 74 needs to be divided by however many means and standard deviations that you have. So here in this case is 2, okay? 74 is 2. And as you can see here, he's using G power to confirm the total sample size is 74. So that's what he's showing you here, 74. Right, and 74. And these are the things that you put in by putting 10, 20, and then size of 10, and then equal N of 5. Standard deviation within each group is 13, okay? Number of groups, 10 and 20, size 10. I'm not sure what size is in this case, but we put in all of the rest of the numbers, and then boom, there you go, 74. So that's what he is explaining here. He also has this set up in the pamlj data, so we can go to open, and we can go, not documents, data library, excuse me, go to power analysis, and there it is, factorial design. And what it does is it opens this one. So this is the factorial design with all of these means and standard deviations in it. So if we were to go to factorial design and we go to means, we go to factors here, put those in, means and SDs, you can see what we need. We need a lot. I would go with the largest number on here, but it really depends on which effect you're looking for. So that's what I would describe. That's what I would explain to everyone who is watching. This isn't for sample size. This is for calculating power. There we go. And sample was 240, he said. 240, he said. And this tells us our sample and then the power that was observed. So this one, expected means, is really useful for determining post hoc power. So you can see that the main effect of A had a very low power. Same with the main effect of B. Our biggest source of power was the main effect of C, which is 0.62. So you can see that sensitivity analysis is really important. But we're going to leave that one there. I do recommend going into this one in case you wanted to follow that a little bit more. For the purposes of this video continuing, I want to use partial eta squared, okay? Partial eta squared. So partial eta squared is the typical effect size that you would see in an ANOVA results section, okay? If it was a single factor, then you might just see eta squared, because partial eta squared and eta squared with a single independent variable or a single factor is going to be the same, right? They're going to be the same. So what values are we thinking about for partial eta squared? Well, 0.2 is a value, right? And I want to show you a particular posting here. Now, this is just one reference that I found. There's a lot of different ways that you can go about an eta squared interpretation: small, medium, large, weak, medium, or weak, moderate, and strong. And these are what I have found. And this is what I share with my students, that an eta squared of 0.01 is a small effect. 0.06 is a medium effect. And 0.14 is actually a very large effect for eta squared, and partial eta squared. Excuse me, there should be a little sub p right here, but resources at National University, maybe they don't know how to do that. But these are values for partial eta squared. I want to be very clear that this is partial eta squared, not necessarily eta squared for ANOVA, okay? So if we've got 0.2 up here, we're looking at a large effect for whatever it is that we are doing, okay? So just keep that in mind as we go through some of this information. Okay, so moving further into the ANOVA design, we have effect information, effect degrees of freedom. This is the value that you would find in a chart, right? An ANOVA source chart. One would reflect, I've got 2 levels of this group. That's what would happen here, right? That's what we would see. So if I put a 2 here, okay, that would mean my ANOVA factor, whether I'm doing a factorial design or a one-way ANOVA design, I've got 3 levels of that variable, okay? So that's 3 levels. So, and as you can see, we have a group that's required here. And what happens is, if you take this group, actually, take that one. If we have degrees of freedom of 1, okay, we need a total n of 45, but an n group of 15. Now, that's 45 divided by 3, but I only have 2 groups. Oh, number of groups in the design is 3. Oh my god. Number of degrees of freedom is going to be based on how many. This should actually, if 3 groups, and I'm looking for my between subjects design information, I definitely want these numbers to coincide, but they may not, right? You could be looking for an interaction. This could be an interaction as a between subjects interaction, which would have a different degrees of freedom value here than would be number of groups. So keep that in mind. That's why they are separate. But I was thinking of a single factor design. I'm sorry. I was thinking of a single factor design. So number of groups should be 3. Number of degrees of freedom should be 2 if we only have one between subjects variable in this model. And that's what we've set up here, okay? And so in actuality, we need 54, and each group is going to have a value, 18 people in it. And the effect size is we're looking for is a partial eta squared of 0.2, and a similar effect size, and this is the one that you need for G power, a similar effect size is called Cohen's F, or Cohen's F squared, and partial eta squared translates to Cohen's F in this manner. 0.2 is an F squared of 0.25. I'm not clear on the distinction between the two, but there you go, okay? Now, with 54 individuals, not only do we have our degrees of freedom value that we put in over here, but we also have our error degrees of freedom value, or residual, as RES indicates here. So that is going to be 54 minus 1 minus 2, which comes out to 51. 51 minus 54 minus 2 is 52, right? Minus an additional degrees of freedom for the single individual who's not allowed to vary. We end up with 51 in the error term of this F statistic that we're looking for. So with our power analysis, all things being equal right here, right? Minimum desired power is a 0.9. Alpha is 0.05. We're not changing that one. You can see that P eta squared, partial eta squared. So they're putting the P in front of it. I guess that's one way to do it. You can see where those effects. But let's look for how many people we need for with these same parameters. Let's go to that partial eta squared. Nope, I added another. Partial eta squared of a small effect, which is 0.01, right? Look at how many more people that we need to detect that effect. Divide that by 3, and we end up with 419. Oh boy. That's not good. But what if this was within subjects variable in our single ANOVA, our one-way ANOVA? Well, we click on within subjects, and what it brings up is this, right? So we have effect is only within. Effect is within between interaction, which is what you need to select if you were looking for your interaction. So a lot of people ask me, which test should I use, Dr. Swan, when I'm doing a factorial ANOVA? And I said, and I always say, well, it depends on what your hypothesis is, right? If you want to do a power analysis and you've got an hypothesis about the interaction, for example, then you do the effect within, you do this, right? Number of groups for the effect, 2 and 2, right? Number of groups and number of groups, these should align. I'm assuming they would. No, they don't. Okay, well, yeah, maybe they don't. So you would do that. But then I also suggest you should always look for the smallest effect. So if you've got a within subjects effect, main effect that you're looking for, right? Within subjects, but the effect is only within, that would be in a main effect, then go with that one. If that's the smallest one, like 0.01 right here, if that's the smallest one, well, that sample size value is going to encapsulate the other ones, right? Because if I go to, so if I've got 2 degrees of freedom and 3 here, and we go back to this, number of groups in the design is 3, and we have 0.01. We need quite a few people, right? 1,200, almost 1,300 people. But if we change this to within subjects and we have degrees of freedom, number of groups is 1, within subjects are inherently more powerful, which means they have more power built within. Fewer people are needed to detect the same effect, right? We needed 1,250 or so to detect a partial eta squared of 0.01. Same parameters as before, 2 degrees of freedom, right? So I have a group of 3, only one group, 0.9 and 0.05. I need half that value. Look at that. I need half that value of the previous one to detect a really, really small effect here, right? 629. And you can see that because I only have one group, that is also 620 0.9. Really good. We multiply 629 by 3, and look at that, 1256. Interesting. To get that degrees of freedom residual, right? 1256 would give us our, ANOVA information or whatever, and you can see that partial eta squared of 0.01 is actually equal to 0.01 for Cohen's f squared. Okay. All right. So that would be a one-way within subjects ANOVA, but you could also do this with interactions. Interactions, of course, require 2 or more variables, but you only get the within between interaction if you do within. So we're going to do effect is within between interaction. Okay, so it's an effect between our between subjects variable and our within subjects variable. We're going to say our between subjects variable has 3 groups. Okay, which as you can see didn't change the value too much. I would like that to be multiplied by 3 instead of that. Where does the extra person go? Yeah. And then the number of groups for the effect would also be 3. I think you should put those in, but the effect degrees of freedom I think applies to the within variable, and the number of groups and groups for the effect applies to the between subjects variable. Perhaps we'll find out more when the pamlj page gets updated, but that's what I'm thinking here because nothing had really changed when I changed these to 3. We need 631 people for this really small effect, and 210 are going to be in each of my between subjects group. It doesn't really matter how many people are in the sample, except for how many people are in the between. And I'm pretty sure if I were to think in Marcelo's shoes, I would say that's why he put it in this way, because a between interaction is going to rely on your largest between subject factor. So if you had a 3x2, for example, the interaction would be based on the sample size needed for the 3 versus the 2. Or you could combine those and be like, how many people do I need? I think that's what this is trying to say, is that it doesn't matter how many people that we have in total, it's how many people need to be in each group to test this partial eta squared, to find out how many people we need to find this really small partial eta squared. And if we change this to 0.14, right, our large effect as I add up, then you can see that we only need about 15 people per group. I would say that needs to be a 45 and needs to be rounded up. But there you go. The effect size would be 0.14 and our f squared would be 0.16. Now we can also change the power that we want. We can drop that down to 0.8. So let's go back to a really small effect, 0.01, okay, and take a look at what this shakes out to. So instead of 630, we need 482 or just 161 per group. Now you're probably saying, wow, Dr. Swan, I need that many people to do this kind of effect? Well, yes, if you're looking for a small effect. If you don't hit this, well, then you might end up with a situation where you're going to detect the effect, right? Because if your partial eta squared in your actual data analysis ends up being bigger than 0.02, guess what? You have a ton of power, right? So you're almost surely to detect it, because it's like what I say about, I use a needle in a haystack method here. We've got a really, really, really small needle, but we've also got a really small, we've got a power of 95% or more. We've got a really small haystack. Like it's just a handful of hay, where the needle is small. Yeah, but we've got a small bale of hay. So that's the idea here. Okay. So yeah, we're looking for a very small effect. It says we need a lot of people, but if the effect is a lot bigger, right? Not 0.16. Let's see how many. We only need 80 people in a group. 27-ish per group. Try to get a total of 80. That's your minimum, by the way. 27 times 3 is 81. Okay, but you might want to hit that. You might want to hit 81, but your minimum is 80 at 0.8 power, right? So here's our value of 0.6 in there somewhere. But if we detect an effect of 0.09, well, then we have a ton of power. So that's how you do the effect size imputation method. Expected means a little janky. I think it's mostly for post hoc power, right? Calculate power instead. We can do a sensitivity analysis by looking at our power plots, right? So we've got 0.8 as our curve that's following this gradient color here. We've got a big old yellow section. We can see that if we're looking for 0.06, bing, here it hits N down here on this line. And if we get those other curves, you can see that, if we hit, let's see, where does it asymptote right there? If we hit like 150, I don't know what's halfway between 114 and 218, but if we go up there, that's pretty much where maybe it's asymptoting somewhere right here, actually. So about 218. If we had a total sample size of 218, then we're going to have 0.99999 power, right? So if our estimated effect size is 0.06. Just saying, that's how you need in log scale if needed, right? So that changed it a little bit. Not necessarily anything we need. You can also create power parameters plots, which show like this, and you can show what happens when two things are different. Like here, I've got 2 lines of effect size by sample size, and you can see blue is 0.05. Orange is 0.1. What happens with them? They're pretty close. There isn't much difference between effect size and sample size. And you can see here that sample size, a very small sample is needed if you're looking for very small effects. This graph is not optimized, I'll say, for the tiny numbers that we're using for partial eta squared, right? Now, I clicked on this a little bit ago, but non-centrality parameters, NCP, I'm not actually sure what this is. Model-based, I think, is a good default, and that's what it's on, but you can also be very liberal, which, okay. Liberal reduces the amount of people that I need by basically 1 per group in that case, or we can be strict, which is very similar to the model-based. Well, there you go. And that's how you do a factorial design power analysis in the pamlj module, pamlj. Stay tuned for the rest of them, where we're going to go over proportions, the GLM, and mediation. I will not be doing the structural equation modeling, sorry. But we've got about 3 more videos left of the series, so I hope to see you in the next one. Please leave your comments, suggestions, questions, and other feedback down in the comment section below. Thanks for watching. Bye.